Okay, welcome ladies and gentlemen to this video lecture. So we now start a new section, and this section is on what is called arc length. So the idea is, if you have some interval AB and you have some function defined on the closed interval AB, how long is the curve given by the graph of this function in between these 2 points AB? So you can think of it as follows. Think of it as an insect walking on this curve, and we ask ourselves, how far did this insect walk if he walks from this point to that point? And of course he walks further than if he would just walk a straight line. So that is the question we want to ask. So what we will do is we will give a definition of arc length, and then we will motivate why this is a good definition. So definition: let f be some function on the closed interval AB to R, and let this function be differentiable. Let it be differentiable on the closed interval AB, and with its derivative continuous on the closed interval AB. Then we define the length of the curve. So the length of the curve, and let's give explicitly a definition of the curve. Remember, what is a curve? A curve is a set of points in the plane. So the curve is the set of points, all the points x, y, with the x coordinates in the closed interval AB, and the corresponding y coordinate equal to the function value. So this is just the graph of the function f on the interval AB. So we define the length of this curve, and now always remember, what is a curve? A curve is a set of points. So here we have written a set of points in set builder notation, and the length of this curve we define as, we use the symbol L, and we define the length as the following integral. So 1 plus the derivative of f of x squared dx. Okay, so here we have given the definition of arc length. So we can use this expression to work out the length of the curve given by the graph of the function f. Okay, so what we will do now is, let us motivate why this is a good definition of arc length. So let us motivate this. So we have already, many weeks ago, we have seen that we can work out the distance between 2 points in R2 or in R3. So if this is point P and that is the point Q, what is this distance? Well, it is the norm of the difference of these 2 points. Okay, so we can work out the length of straight line segments, but now we want to work out the length of curved segments. So what will we do? Here we've got, let's say we've got an interval AB, and we've got some curve which is the graph of a function f on AB. So we've got some function f defined on AB into the real line. And what will we do now? Why don't we approximate this curve by straight line segments? So what we will do is we will subdivide this interval into n equal parts. So let's again subdivide our interval AB into n equal parts, and then what we will do is we will look at these points here, and we will connect these points by maybe I should use a different color, purple. We will connect these points by straight line segments, and we will use the length of these straight line segments as an approximation for the length of the curve. And let's see what we get. So let us define delta x. So delta x will be the length of each of these little subintervals, and what is that? That is b minus a over n. So if we divide our interval into n parts, what is the length of each one of these little intervals? That is, we define the symbol delta x, and what is delta x? That's the length of each one of them, so that is the length of the total divided by n. And let us also define the point xj. So xj is that will be each one of these endpoints of our subdivision. So we start with x0, x1, x2, etc. So xj will be a times j times delta x, where j is any number from 1 up to n minus 1. And let us define the points pj. So pj we will define as each one of these points in R2. So pj, that is a point in R2, has coordinates xj, and what is its y coordinate? fxj. So each one of these points, so this will be the point p0, this will be the point p1, this will be the point p2, etc. So it has, these are points in R2, so they have two coordinates. What is their x coordinate? Is the x coordinate, and what is the y coordinate? That is just the function value. Okay, so let us use the length of these straight line segments as an approximation for the length of the curve. So let us, what is, if we add up all these straight line segments, or the length of all of these straight line segments, that will be an approximation for the length of the curve. So the an approximation that is misspelled. Approximation of the length of the curve that is also misspelled. Curve. That is, so what is an approximation? An approximation is going to be the sum from j to n minus 1 of what? This will be pj plus 1 minus pj. So the norms of these vectors. And if you just think about what this is, so what is this? This is the sum of, if j is equal to 0, this is going to be the length of the curve from P1 to P0, or otherwise the length of the straight line segment from P0 to P1. So this length. So if j is equal to 1, the term in our summation is this length. And if j is equal to 1, then it is the length of the curve from P1 to P2, etc. And we add up all of those up to n minus 1. Okay, so let us write out exactly what this is. So let's just expand the definition of everything. So this is the square root of xj plus 1 minus xj squared plus the function values fxj plus 1 minus fxj all squared. Okay, but what is this? This is the difference between the x coordinates of these points. So it is, in fact, it is this distance, and we define that to be delta x. So this is actually the square root of delta x squared plus fxj plus 1 minus fxj all squared. Okay, let us take out this delta x squared from this square root. So we've got the sum from j 0 to n minus 1. Take it out. Delta x is positive anyway, so we don't need to worry about that. So the square root of the square is absolute value, but delta x is positive anyway. So what are we left with? We are left with the following. We are left with, and I'm going to write it like so, fxj plus 1 minus fxj over delta x squared. Okay, but I'm going to rewrite this delta x as xj plus 1 minus xj. Okay, so far so good. This expression you should recognize. So what is this? This is the slope of the line segment connecting these 2 points. So if you go think about what each one of those expressions are, that is the slope of this line segment for each one of them. So, and now using the differential mean value theorem, so by the differential mean value theorem, so what does the differential mean value theorem say? It says if you've got some appropriate function and you connect the endpoints and you look at the line segment connecting the endpoints of this function, then there exists a point on the graph of this function where the slope of the graph is exactly the same as the slope of the line segment connecting to the 2 endpoints. So there exists some what we call xj star in the interval, in the open interval xj to xj plus 1 with this expression fx j plus 1 minus fxj over xj plus 1 minus minus xj, with this expression equal to the derivative of f at the point xj star. So if we use this, what do we get? This expression, if we rewrite it, so replace this part with the with this part, what do we get? This is then equal to the sum j from 0 to n minus 1 of delta x 1 plus the derivative at xj star squared. And let's put this delta x at the end here. Delta x. Okay. But this is something you should recognize. We've got something multiplied with a delta x, and then we're adding up a whole bunch of terms here. So this is a Riemann sum which approximates a certain integral. So this is a Riemann sum which approximates the following integral. So integral from a to b of 1 plus derivative of fx squared dx. And you will see that this is exactly the expression that we used to define our arc length. So just to reiterate, how did we get there? What did we do? We took our curve. Maybe I should make a new diagram. So just to reiterate, how did we get there? We took our curve and we subdivided it into n equal parts, and we approximated the length of our curve by the straight line segments connecting the endpoints of our subdivisions. And we saw that if we now add up the length of each one of these straight line segments, which we know how to work out the length of, if we add up all these lengths, what we end up with is a Riemann sum that approximates the integral that we defined our arc length with. So in fact, if we subdivide our interval into even smaller sections, we get a better approximation for the curve, and then in the limit, that approximation will then be equal to this integral, and that is the expression that we use to define arc length. Okay, so this is a motivation for arc length. In the next one, we will do an example. I will see you in the next one.